So this is a case of X-bar and MR charts. This is the last one in the series. MR actually stands for the moving range. Okay, this is a control charts for the individuals. So again, this is a case for n equal to number 1. Think about what does this look like. Say standard error is nothing but square root n sigma. When the sample size is equal to 1, right, is equal to 1, your standard error is basically the population standard deviation. So you're actually plotting the population as it happens, right? Think about occasions where this type of plotting is necessary and important. So for example, the Center for Disease Control, they may have to report the number of infections from from this particular disease in a weekly basis. Okay, this is total. You're reporting number of infections from certain disease in a weekly basis or even daily basis. Okay, sometimes even a week may be too long to report certain certain disease. So in that case, if you're choosing waiting 5 days and report the average, or at the end of the day you're reporting the daily total, so this makes huge difference. Okay, so the challenge of reporting it as it happens is that we don't have a good estimator for the process variations, where if you think about when f sample size is number 5, you may have one observation is here, the other here, the other here, the other here, and we've learned we measure the range, the highest with the lowest as the approximation for the process variation. We multiply with D3 or D4 to obtain the process variation estimates. But when you have only one sample, that is just simply not possible. Okay, so that is why we need to utilize this special chart called a moving range charts. So moving range charts tracks the moving range of n successive observations. Okay, so not to be confused this n with this n. Okay, when we plot the chart, we use sample size number 1. However, to calculate the range, we are observing n successive observations. Okay, let me show you what that is in the upcoming exercise. So here is the control limit calculation. Here is again X charts control limit. So I think let's move on. So this exercise here, measuring the percentage of cobalt in a chemical process as given in the figure below, the moving range with 2 is determined appropriate. So in other words, to calculate the average range, what we're going to do is we're going to take first 2 observations, right? We calculate the range. And next 2 observations, we calculate the range. Next 2 observations, 0.5. Okay, remember that I'm only reporting in the positive numbers because you're going to take the absolute value, absolute difference here as the range. Okay, so if you're picking n equals 3, that means what you're going to do is you're picking 3 numbers as a group, right? And here the range is going to be 0.10. Next 3 is these 3 guys. In this case average range, no, in this case range is 0.60, and then next 3.7 all the way to 3.5, you're seeing range of 50 and so forth. You keep doing it. Okay, so at a certain point you will see that there's a big jump in this number. That may be an indication that something has happened in the underlying process. So with that, let's move on to Excel to finish this chapter once and for all. Okay, so here as you can see that I've done some pre-calculation here. However, let's not talk about however for now. So range group is 2. So what I've done here is I've done B3 minus B2. You got this number. Okay, let me redo it just to show you. This minus this. Okay. Yeah, we got all these ranges ready, but we need to take the absolute value of these guys, so that we only take the positive, because we're only trying to measure the difference between highest and lowest. Okay, so the average of all the ranges is going to be So you have R bar ready as this. Okay, remember you cannot calculate X bar here. Okay, LCL MR is going to be lower control limit for the R bar. We are multiplying this vector with, no, we're just multiplying the R bar with the vector D3. Okay, again, we're just going to multiply D4 with the R bar value. So this is our range. Okay, as long as the process doesn't show any greater jump than 1.15, we assume that our process variability is within control. Okay, with that in control, let's take a look at the X bar. So X bar here is basically the average of all the outcome here. Okay, so with that, lower control limit, 3 multiply R bar divided by D2. Okay, again, X bar plus 3 multiply R bar divided by D2. Voila, we got it. So you got X bar chart here, you got moving range bar here. Okay, so that kind of concludes this last component. Of course, when you have 26th observation or 27th observation, you are of course comparing with these to see whether the process is in control or out of control. So we've studied quite a bit here in this particular day. Here is a summary of all the exercises. If you look at this exercise number 1 and 2, it's actually how to plot X bar and R charts. Okay, there's more than one exercise because I wanted you to take a look at how this thing actually works. So the second exercise is actually a case from your textbook. I'm not sure how much you have understood from the case that I have demonstrated. If you need more information, please feel free to review your textbook about this case. Okay, and then number 3 is about the X bar and S, and number 4 is MR charts. Again, R, S, or MR depends on the size of sample you're using. Okay, so this case is sample size is between 1 to 10. In this case, sample size is larger than 10. In this case, sample size is exactly equal to 1. Okay. Yep, I hope you have digested what I've demonstrated here. Is really techniques to calculate the upper control and lower control limit for both process variability and the process average. Okay, so we are going to study this part coming Thursday. Okay, thank you.